Thank you for organizing this event and letting me to speak here. So today I'm going to talk about logarithmic Sobolev inequalities on non-isotropic Heisenberg groups. So in this talk, I will mainly focus on the constant inside this inequality, especially the dimension independence of the constant, since there are a lot of infinite dimensional applications of this dimension independence. So let me first recall the log Sobolev inequality on Rn. Here I'm giving the analytic form of this inequality. So we take the Gaussian measure on Rn, whose Radon-Nicotin derivative is the heat kernel at the time t equals 1 on Rn. And then we have such an inequality of this form. The entropy is bounded by a constant C times the Fisher information. And here the constant inside this inequality is independent of the dimension n. So what's behind this inequality is the ellipticity of the generator, which is the Laplacian operator on Rn, and also the smoothness of the heat kernel is needed for your measure. But last but not the least, the constant here does depend on the Ricci lower bound of your underlying space. And on Rn, as we know, the curvature is 0. So what if when you come to some spaces whose Ricci lower bound may blows up to negative infinity in certain direction, and that is the starting point of our work. And what we are considering non-isotropic Heisenberg groups are one of those models. So the Hn omega can be regarded as a set of R2n plus 1, but equipped with a non-commutative law like this. So you still keep the first 2n copies commutative, same Euclidean law, and the last one you make it non-commutative by such a symplectic bilinear form omega. Linear algebra tells us that omega can be simplified into such a form by those positive real numbers alpha I. So you got n alpha i's. So here we note that what we are considering are actually a family of non-isotropic Heisenberg groups. They are labeled by the symplectic bilinear form omega. Also, when we take all those alpha i's to be equal, and that is the so-called standard Heisenberg group. On this Lie group, we can take, the left invariant vector fields xi omega and yi omega. You can see that the Lie bracket between each xi omega and yi omega gives the alpha I times the z vector field. So this means at every point on your Lie group, the tangent space at that point can be generated by all those xi omega and yi omega under the Lie brackets. So Homander's condition is satisfied in this situation. An important consequence of Homander's condition is the following. When you consider this operator, we call it sub-Laplacian, which is just the sum of the squares of vector fields xi omega and yi omega. This operator is hypoelliptic. And for the hypoellipticity of this operator, you can just think of the regularity estimate in the elliptic PDE theory. This just means the situation we are considering here is much weaker than the classic elliptic case. Just a little remark about the geometric structure of Hn omega. There is a natural sub-Riemannian structure on non-isotropic Heisenberg groups. Here, what it means for sub-Riemannian is that instead of the complete tangent space at every point, we will just look at a subspace of the tangent space in this setting, this subspace is just the vector space spanned by those xi omega and yi omega. The sub-Riemannian metric is on the this subspace at every point. And here the nabla omega h is the horizontal gradient. So with the structure given, we would also like to consider a hypoelliptic log Sobolev inequality on the non-isotropic Heisenberg group of a very similar form. So here, instead of the Gaussian measure, we will consider the heat kernel measure, whose Radon-Nicotin derivative with respect to the Haar measure is the heat kernel for the sub-Laplacian on Hn omega. So we will ask, on this family of Heisenberg groups, can we find such a uniform constant C such that the hypoelliptic log Sobolev inequality still holds? If it does the constant C depend on the dimension in this setting? However, as we know, our setting is much weaker. It's the hypoelliptic case. So a lot of nice elliptic theory may not work. And in this situation, functional inequalities may be harder to prove, but still we got the smoothness of this heat kernel. Here are some literature selected reference, but most of those work is done in the standard case when all those alphas are equal. However, not too much has been addressed about the dependence of this constant on the symplectic bilinear form omega, or even when you go to the non-isotropic case, not too much is known about the dimension dependence of the constant inside this inequality. And this is what we studied. So we studied this family of non-isotropic Heisenberg groups, and we showed that there is such a log Sobolev inequality with a uniform C over all those symplectic bilinear form omega. And what's more, we studied the dependence of this constant on its underlying geometry, the omega, and we showed that this C is indeed independent of the symplectic bilinear form. And what's more, we get the dimension independence of this constant C. So I still have a few time left, so I will mention briefly about the idea of our proof. The idea of the proof relies on the tensorization-like structure of non-isotropic Heisenberg groups. So we would like to regard it, the group, as a quotient group of a product of n copies of three-dimensional Heisenberg groups. So to start with, we will consider the log Sobolev on the three-dimensional non-isotropic Heisenberg group. To compare this three-dimensional non-isotropic Heisenberg group with the standard case, we are able to get a log Sobolev on this H1 omega. And at the same time, we can show that this constant C, when n equals 1, is already independent of the symplectic bilinear form omega. And what's more, this C is actually the same as the one on the standard Heisenberg group. And next, we will go to the product space of n copies of H1 omega. So here inside this product group, you can take different symplectic form omega j, it's okay. And we will study the tensorization of log Sobolev inequalities in this sub-Riemannian setting. And in this case, we get on the product group, you can have a log Sobolev, and the constant C is actually the same as the one on each H1 omega j. So you don't see any effect when you add those different symplectic bilinear form omega j's. The last step is to go from the product group to the non-isotropic Heisenberg group for higher dimension n. So to do so, we will build such a map pi from the product group to Hn omega. And this enables us to push the log Sobolev on the product space to the Hn omega. And this map just collapses the center of the product group into a one-dimensional center on this Hn omega. What we get is the following. The map pi push the log Sobolev from the product space to Hn omega, the non-isotropic Heisenberg group, and at the same time, it keeps the constant c. So this means from the previous two steps, we know that the constant c on the product space is already independent of all those alpha i's, and therefore we get the independence of the constant in the non-isotropic case when n is greater than 1. And at the same time, we will get the dimension independence of the constant as well. So in the end, I'll give some further directions as the following. And that is all. Thank you very much.
Okay, so I'll stop the recording and I'll open the floor to a question.